control the speed of our motor, it seems like we need an analog signal out of the Arduino because speed can go from 0 to maximum, and you might want to be able to set it to many, many levels in between. Seems like then what we need is the opposite of the analog to digital converter that takes an analog voltage in the outside world, remember, turns it into a digital value in the Arduino. We need the opposite function. We need to take a digital value in the Arduino and produce an analog voltage out in the outside world. Such circuits exist. They're called, cleverly, digital to analog converters. Unfortunately, the circuit area required for those on the chip is pretty big. And our itty-bitty Atmega processors here didn't have that area, so we don't have that. Fortunately, that doesn't mean we're done. There's a way, very clever way, that we can get analog control of our motor speed and many other circuits without needing that digital to analog converter, and we can do it through a special and clever use of a digital output line. And this seems to make no sense because digital and analog are different things, and the key idea, which we'll go through in detail here, is instead of changing a constant voltage, we could take a certain period of time, and within that time we could make the voltage high for a certain amount of time, digitally high, and low for another amount of time. And then if we averaged over that, if we are on for a little bit of time and off for a lot, that's effectively an average voltage which is low. So we're going to change the width of our pulses out of a digital line, not their analog amplitude. And for instruments that can understand that, that gives us effectively an analog signal that we're only using small area, cheap digital circuitry to do it. So let's walk it through and see how that works. The command to do this in the Arduino language, the sketch language, is analogWrite. It looks like the same family of analog read, digital write, things like that. It takes two parameters, the digital pin, and it is a digital pin, that you're going to use, and some other number. So let's see what that number is. Let's imagine that we loaded up our Arduino, we execute that command, and we'll put an oscilloscope on pin 9 and see what the signal is. So if we execute the command here with a 0 as the parameter, what we see is what looks like a digital signal that's off. It's 0, it doesn't do anything. So kind of boring, but apparently that's gotten us at least one speed value for our motor, which is 0. So that's something. Let's call the function with a different number though, maybe 64. It is an integer, so that makes sense. Now our scope will show us this interesting waveform. It's a square wave, but it's on for 25% of the total period. We'll call that a 25% duty cycle. Duty cycle just means the ratio of the on time to the total time in each period. And if the system that we drove this signal into responded to the average value within each period, then we've actually got something here which is an average that's 25% of the way from the bottom to the top, and that's starting to look like an analog signal. Our motor does do this because the period of this signal is much faster than the rotor is rotating. This is actually directly what's driven into the motor, and the motor does the averaging. Because when this signal is high and on, the electromagnet is energized, the magnetic field in the rotor is attracting that rotor to the static fields of the stator, and then for 75% of the time it turns off, and we're simply not pushing on it, and then it turns back on, and then it turns back off. So it's like instead of driving the motor with a small voltage, which would give a small force, instead we're hitting it with a large force, the largest the motor can provide, for some amount of time, and then saying, oh, not. So it's like we're kicking the rotor down, to turn, but the rotor moves so slowly, it just averages over all this. It doesn't go tick, 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 tick. It's this big mechanical system with its own time constants that are much larger than this period, so it effectively averages this signal, and we get the analog response that we want. If we increase the number, we'll see the duty cycle increase, the width of the pulses increase. This is why it's pulse width modulation. To modulate is to change. So the 128 here has changed the duty cycle to 50% on and 50% off. And if we increase the number some more, now we see it's on for 75% of the time. So the motor is going to start spinning faster because we're pushing it more often. And finally at 255, we'll see what looks like a digital signal that's on all the time. So the number here clearly is a scaled value, the digital value that we want to have inside the Arduino that's controlling the quasi-analog value outside, controlling the motor value. This has only 8 bits of resolution, so therefore 256 levels, as opposed to the analog to digital converter, which has 1024 levels, 10 bits. And so, okay, this particular system has a little bit more granularity, has a little less precision, but it's usually enough to have 256 different, in this case, motor speeds, and this is how the system works. It's very clever. There's many, many devices that will understand this pulse width modulation because it's simply a much cheaper system in terms of chip area and complexity to use this digital line, and the fact that digital signals we can turn on and off really fast. We exploit that to make a system that looks like analog but doesn't actually change the analog value.